The Wide Area Augmentation System is an air navigation aid developed by the Federal Aviation Administration to augment the global positioning system, with the goal of improving its accuracy, integrity, and availability. Essentially, WAAS is intended to enable aircraft to rely on GPS for all phases of flight, including precision approaches to any airport within its coverage area. WAAS uses a network of ground-based reference stations, in North America and Hawaii, to measure small variations in the GPS satellite signals in the Western Hemisphere. Measurements from the reference stations are routed to master stations, which cue the received deviation correction and send the correction messages to geostationary WAAS satellites in a timely manner. Those satellites broadcast the correction messages back to Earth, where WAAS-enabled GPS receivers use the corrections while computing their positions to improve accuracy. The International Civil Aviation Organization calls this type of system a satellite-based augmentation system. Europe and Asia are developing their own SBASs, the Indian GPS-aided George Augmented Navigation, the European Geostationary Navigation Overlay Service and the Japanese Multifunctional Satellite Augmentation System, respectively. Commercial systems include Starfire and OmniStar. WAAS objectives. Accuracy. The WAAS specification requires it to provide a position accuracy of 7.6 meters or better, at least 95% of the time. Actual performance measurements of the system at specific locations have shown it typically provides better than 1.0 meter laterally and 1.5 meters vertically throughout most of the contiguous United States and large parts of Canada and Alaska. With these results, WAAS is capable of achieving the required Category I precision approach accuracy of 16 meters laterally and 4.0 meters vertically. Integrity. Integrity of a navigation system includes the ability to provide timely warnings when its signal is providing misleading data that could potentially create hazards. The WAAS specification requires the system detect errors in the GPS or WAAS network and notify users within 6.2 seconds. Certifying that WAAS is safe for instrument flight rules requires proving there is only an extremely small probability that an error exceeding the requirements for accuracy will go undetected. Specifically, the probability is stated as 1A, 10^7, and is equivalent to no more than 3 seconds of bad data per year. This provides integrity information equivalent to or better than receiver autonomous integrity monitoring. Availability. Availability is the probability that a navigation system meets the accuracy and integrity requirements. Before the advent of WAAS, GPS specifications allowed for system unavailability for as much as a total time of 4 days per year. The WAAS specification mandates availability as 99.999% throughout the service area, equivalent to a downtime of just over 5 minutes per year. Operation. As with GPS in general, WAAS is composed of 3 main segments: the ground segment, space segment, and user segment. Ground segment. The ground segment is composed of multiple wide-area reference stations. These precisely surveyed ground stations monitor and collect information on the GPS signals, then send their data to 3 wide-area master stations using a terrestrial communications network. The reference stations also monitor signals from WAAS geostationary satellites, providing integrity information regarding them as well. As of October 2007 there were 38 WRSs, 20 in the contiguous United States, 7 in Alaska, 1 in Hawaii, 1 in Puerto Rico, 5 in Mexico, and 4 in Canada. Using the data from the WRS sites, the WMSs generate 2 different sets of corrections, fast and slow. The fast corrections are for errors which are changing rapidly and primarily concern the GPS satellite's instantaneous positions and clock errors. These corrections are considered user position independent, which means they can be applied instantly by any receiver inside the WAAS broadcast footprint. The slow corrections include long-term ephemeric and clock error estimates, as well as ionospheric delay information. WAAS supplies delay corrections for a number of points across the WAAS service area. Once these correction messages are generated, the WMSs send them to two pairs of ground upper-link stations, which then transmit to satellites in the space segment for rebroadcast to the user segment. Reference stations: each FAA Air Route Traffic Control Center in the 50 states has a WAAS reference station, except for Indianapolis. There are also stations positioned in Canada, Mexico and Puerto Rico. See list of WAAS reference stations for the coordinates of the individual receiving antennas. Space segment: the space segment consists of multiple geosynchronous communication satellites which broadcast the correction messages generated by the WAAS master stations for reception by the user segment. The satellites also broadcast the same type of range information as normal GPS satellites, effectively increasing the number of satellites available for a position fix. The space segment consists of three commercial satellites, Inmarsat 4F3, Telsat's Anik F1R, and Intelsat's Galaxy 15. The original two WAAS satellites, named Pacific Ocean Region and Atlantic Ocean Region West, were leased space on Inmarsat 3 satellites. These satellites ceased WAAS transmissions on July 31, 2007. With the end of the Inmarsat lease approaching, two new satellites were launched in late 2005. Galaxy 15 is a PanAmSat, and Anik F1R is a Telsat. As with the previous satellites, these are leased services under the FAA's Geostationary Satellite Communications Control Segment contract with Lockheed Martin for WAAS Geostationary Satellite Leased Services, who is contracted to provide up to 3 satellites through the year 2016. A third satellite was later added to the system. From March to November 2010, the FAA broadcast a WAAS test signal on a leased transponder on the Inmarsat 4F3 satellite. The test signal was not usable for navigation, but could be received and was reported with the identification numbers PRN 133. In November 2010, the signal was certified as operational and made available for navigation. The Galaxy 15 satellite ceased responding to control commands between April 5, 2010, when solar activity damaged the spacecraft unregistered trademark S communication package, and December 23, 2010, when its battery drained and the baseband equipment command unit reset. During this time, the satellite drifted from its original location of 133 degrees west to 93 degrees west, but the WAAS signal continued to be broadcast until December 16, 2010. Since Inmarsat 4F3 is to the east of Anik F1R, this left 16 airports in northwest Alaska experiencing temporary service outages 4 to 5 times a month due to lack of redundant WAAS signals. By January 2011, Intelsat expected to be able to return the Galaxy 15 satellite to its original location by early March 2011. As of 3:24 p.m. U.S. Eastern Time on March 18, 2011, Galaxy 15 was once again transmitting WAAS signals from 120 degrees west, moving west at 0.8 degrees longitude per day, and expected to arrive at its assigned geostationary orbit at 133.1 degrees west on April 4, 2011. In the table above, PRN is the satellite's actual pseudo-random noise code. NMEA is the satellite number sent by some receivers when outputting satellite information. User segment: the user segment is the GPS and WAAS receiver, which uses the information broadcast from each GPS satellite to determine its location and the current time, and receives the WAAS corrections from the space segment. The two types of correction messages received are used in different ways. The GPS receiver can immediately apply the fast type of correction data, which includes the corrected satellite position and clock data, and determines its current location using normal GPS calculations. Once an approximate position fix is obtained, the receiver begins to use the slow corrections to improve its accuracy. Among the slow correction data is the ionospheric delay. As the GPS signal travels from the satellite to the receiver, it passes through the ionosphere. The receiver calculates the location where the signal pierced the ionosphere and, if it has received an ionospheric delay value for that location, corrects for the error the ionosphere created. While the slow data can be updated every minute if necessary, ephemeris errors and ionosphere errors do not change this frequently, so they are only updated every 2 minutes and are considered valid for up to 6 minutes. History and development. The WAAS was jointly developed by the United States Department of Transportation and the Federal Aviation Administration as part of the Federal Radio Navigation Program, beginning in 1994, to provide performance comparable to Category 1 instrument landing system for all aircraft possessing the appropriately certified equipment. Without WAAS, ionospheric disturbances, clock drift, and satellite orbit errors create too much error and uncertainty in the GPS signal to meet the requirements for a precision approach. A precision approach includes altitude information and provides course guidance, distance from the runway, and elevation information at all points along the approach, usually down to lower altitudes and weather minimums than non-precision approaches. Prior to the WAAS, the U.S. National Airspace System did not have the ability to provide lateral and vertical navigation for precision approaches for all users at all locations. The traditional system for precision approaches is the instrument landing system, which used a series of radio transmitters each broadcasting a single signal to the aircraft. This complex series of radios needs to be installed at every runway end, some off-site, along a line extended from the runway center line, making the implementation of a precision approach both difficult and very expensive. For some time the FAA and NASA developed a much improved system, the microwave landing system. The entire MLS system for a particular approach was isolated in 1 or 2 boxes located beside the runway, dramatically reducing the cost of implementation. MLS also offered a number of practical advantages that eased traffic considerations, both for aircraft and radio channels. Unfortunately, MLS would also require every airport and aircraft to upgrade their equipment. During the development of MLS, consumer GPS receivers of various quality started appearing. GPS offered a huge number of advantages to the pilot, combining all of an aircraft's long-distance navigation systems into a single easy-to-use system, often small enough to be handheld. Deploying an aircraft navigation system based on GPS was largely a problem of developing new techniques and standards, as opposed to new equipment. The FAA started planning to shut down their existing long-distance systems in favor of GPS. This left the problem of approaches, however. GPS is simply not accurate enough to replace ILS systems. Typical accuracy is about 15 meters, whereas even a CAT-A approach, the least demanding, requires a vertical accuracy of 4 meters. This inaccuracy in GPS is mostly due to large billows in the ionosphere, which slow the radio signal from the satellites by a random amount. Since GPS relies on timing the signals to measure distances, this slowing of the signal makes the satellite appear farther away. The billows move slowly, and can be characterized using a variety of methods from the ground, or by examining the GPS signals themselves. By broadcasting this information to GPS receivers every minute or so, this source of error can be significantly reduced. This led to the concept of differential GPS, which used separate radio systems to broadcast the correction signal to receivers. Aircraft could then install a receiver which would be plugged into the GPS unit, the signal being broadcast on a variety of frequencies for different users. Unfortunately, broadcasters of the required power generally cluster around larger cities, making such DGPS systems less useful for wide area navigation. Additionally, most radio signals are either line of sight, or can be distorted by the ground, which made DGPS difficult to use as a precision approach system or when flying low for other reasons. The FAA considered systems that could allow the same correction signals to be broadcast over a much wider area, such as from a satellite, leading directly to WAAS. Since a GPS unit already consists of a satellite receiver, it made much more sense to send out the correction signals on the same frequencies used by GPS units, than to use an entirely separate system and thereby double the probability of failure. In addition to lowering implementation costs by piggybacking on a planned satellite launch, this also allowed the signal to be broadcast from geostationary orbit, which meant a small number of satellites could cover all of North America. On July 10, 2003, the WAAS signal was activated for general aviation, covering 95% of the United States, and portions of Alaska offering 350 feet minimums. On January 17, 2008, Alabama-based Hickok & Associates became the first designer of helicopter WAAS with localizer performance and localizer performance with vertical guidance approaches, and the only entity with FAA-approved criteria. This helicopter WAAS criteria offers as low as 250-foot minimums and decreased visibility requirements to enable missions previously not possible. On April 1, 2009, FAA AFS 400 approved the first 3 helicopter WAAS GPS approach procedures for Hickok & Associates customer California Shock Trauma Air Rescue. Since then they have designed many approved WAAS helicopter approaches for various EMS hospitals and air providers, within the United States as well as in other countries and continents. On December 30, 2009, Seattle-based Horizon Air flew the first scheduled passenger service flight using WAAS with LPV on Flight 2014, a Portland to Seattle flight operated by a Bombardier Q400 with the WAAS FMS from Universal Avionics. The airline, in partnership with the FAA, will outfit 7 Q400 aircraft with WAAS and share flight data to better determine the suitability of WAAS in scheduled air service applications. Timeline. Comparison of accuracy, benefits. WAAS addresses all of the navigation problem, providing highly accurate positioning that is extremely easy to use, for the cost of a single receiver installed on the aircraft. Ground and space-based infrastructure is relatively limited, and no on-airport system is needed. WAAS allows a precision approach to be published for any airport, for the cost of developing the procedures and publishing the new approach plates. This means that almost any airport can have a precision approach and the cost of implementation is dramatically reduced. Additionally, WAAS works just as well between airports. This allows the aircraft to fly directly from one airport to another, as opposed to following routes based on ground-based signals. This can cut route distances considerably in some cases, saving both time and fuel. In addition, because of its ability to provide information on the accuracy of each GPS satellite's information, aircraft equipped with WAAS are permitted to fly at lower en route altitudes than was possible with ground-based systems, which were often blocked by terrain of varying elevation. This enables pilots to safely fly at lower altitudes, not having to rely on ground-based systems. For unpressurized aircraft, this conserves oxygen and enhances safety. The above benefits create not only convenience, but also have the potential to generate significant cost savings. The cost to provide the WAAS signal, serving all 5,400 public use airports, is just under $50 million per year. In comparison, the current ground-based systems such as the Instrument Landing System, installed at only 600 airports, cost $82 million in annual maintenance. Without ground navigation hardware to purchase, the total cost of publishing a runway's WAAS approach is approximately $50,000. Compared to the $1 million to $1,500,000 cost to install an ILS radio system. Further savings can come from the nighttime closure of airport towers with a low volume of traffic. The FAA is reviewing 48 towers for such a potential reduction of services, which it estimates will save around $100,000 per year at each tower, for a total annual savings of nearly $5 million. Drawbacks and limitations. For all its benefits, WAAS is not without drawbacks and critical limitations. Space weather. All man-made satellite systems are subject to space weather and space debris threats. For example, a solar superstorm event composed of an extremely large and fast earthbound coronal mass ejection could disable the geosynchronous or GPS satellite elements of WAAS. The broadcasting satellites are geostationary, which causes them to be less than 10 degrees above the horizon for locations north of 71.4 degree latitude. This means aircraft in areas of Alaska or northern Canada may have difficulty maintaining a lock on the WAAS signal. To calculate an ionospheric grid points delay, that point must be located between a satellite and a reference station. The low number of satellites and ground stations limit the number of points which can be calculated. Aircraft conducting WAAS approaches must possess certified GPS receivers, which are much more expensive than non-certified units. In 2006, Garmin's least expensive certified receiver, the GNS 430W, had a suggested retail price of $10,750. WAAS is not capable of the accuracies required for Category 2 or 3 ILS approaches. Thus, WAAS is not a sole solution and either existing ILS equipment must be maintained or it must be replaced by new systems, such as the Local Area Augmentation System. WAAS localizer performance with vertical guidance approaches with 200-foot minimums will not be published for airports without medium-intensity lighting, precision runway markings and a parallel taxiway. Smaller airports, which currently may not have these features, would have to upgrade their facilities or require pilots to use higher minimums. As precision increases and error approaches zero, the navigation paradox states that there is an increased collision risk, as the likelihood of two craft occupying the same space on the shortest distance line between two navigational points has increased. Future of WAAS, improvement to aviation operations. In 2007, WAAS vertical guidance was projected to be available nearly all the time, and its coverage encompasses the full continental U.S., most of Alaska, northern Mexico, and southern Canada. At that time, the accuracy of WAAS would meet or exceed the requirements for Category 1 Israeli New Shekel approaches, namely, three-dimensional position information down to 200 feet above touchdown zone elevation. With these projections, the FAA announced on March 24, 2006 that the first procedures that allow operations down to 200 feet would be published in 2007. Software improvements, to be implemented by September 2008, significantly improve signal availability of vertical guidance throughout the CONUS and Alaska. Area covered by the 95% available LPV solution in Alaska improves from 62% to 86%. And in the CONUS, the 100% availability LPV 200 coverage rises from 48% to 84%, with 100% coverage of the LPV solution. Space segment upgrades, both Galaxy 15 and Anik F1 contain an L1 and L5 GPS payload. This means they will potentially be usable with the L5 modernized GPS signals when the new signals and receivers become available. With L5, avionics will be able to use a combination of signals to provide the most accurate service possible, thereby increasing availability of the service. These avionics systems will use ionospheric corrections broadcast by WAAS, or self-generated onboard dual-frequency corrections, depending on which one is more accurate. See also, Satellite-Based Augmentation System, EGNOS, the European Operational SBAS, Quasi-Zenith Satellite System, the proposed Japanese SBAS, GPS and Geo-Augmented Navigation, the Indian SBAS, currently under implementation. CDGPS Canadian Differential GPS, Local Area Augmentation System, Joint Precision Approach and Landing System, Distance Measuring Equipment, Instrument Flight Rules, Instrument Landing System, Long-Range Radio Navigation, Microwave Landing System, Non-Directional Beacon, Tactical Air Navigation System, Transponder Landing System, VHF Omnidirectional Range, Localizer Performance with Vertical Guidance. References: U.S. Department of Transportation and Federal Aviation Administration, Specification for the Wide Area Augmentation System. External links: FAA WJHTC's Real-Time Interactive WAAS Performance Display, FAA's WAAS Program, Garmin's What is WAAS? U.S. Government's 2005 Federal Radio Navigation Plan, WAAS coverage in Canada.